Let's just play with it a little bit. Let's imagine we have two vectors given to us. In this case, A and B. A is given to us as a magnitude of 3, B as a magnitude of 4, and you will see that angles are given for each. So let's summarize vectors if you haven't read the lectures yet. Vectors can have two properties, magnitude and direction, and they are just what we need to describe the vector entirely. Magnitude, direction. Graphically, a vector can be represented by an arrow. So the length of the arrow is the magnitude. 3, 4, 5. 1, 2, 3 mark. So that's the length. So that has to be positive. Can always be positive. No worries. No worries, Henry. I don't know either. There is no, you would think that big company would have thought of including an eraser, but no. So I have to change the color and rewrite on top of it. Don't worry. So that's the magnitude. That's the length of the arrow. The direction, 30 degree, 180 degree, obviously refers to where the arrow points towards. Now, of course, in this case, I don't know what the direction of my little vector A is. Because for me to be able to understand direction, I need a reference frame. That's the reason why we need a coordinate system. We're going to work in 2D and 3D in this class, and we're always going to use a coordinate system which is orthonormal, which means that both axes are perpendicular to one another, and this will allow us to use all the trig that we've learned in Math 140, Pythagorean theorem, sine, cosine, blah, blah, blah. And the unit vector, or the scale, is going to be the same. Now, of course, we will be able to rotate them, but the relationship between x and y, to make our life easy, is going to be perpendicular to one another with the same scale. The convention is that the unit vector along the x that has the units of my scale is going to be denoted as I, with a little hat. The little hat tells us that this specific vector I is a unit vector, which means its length is 1. Similarly, by convention, we will use J to represent the unit vector along the y direction. So, once we have the coordinate system, then the direction takes some meaning. For example, 30 degree or 180 degree. When you see a direction given to you with no other explanation, you can always assume that this direction is being measured from the positive x going counterclockwise. For example, 30. So, vector A has a length of 3. 3 of those units, or little scale, and direction of 30 from the positive x going counterclockwise. All right. What's the difference between a vector and a scalar? One is a subgroup of the other one, or a sub-ensemble. Scalar is just a stupid number. 1, 2, 3, minus 1, negative 1.2, whatever. A vector has two properties again, magnitude and direction. The magnitude is represented by a scalar, just the length. But the vector has something else additional, which is its direction, which is denoted by this little arrow. So obviously this vector A is different from this vector, even though they have the same length, 1, 2, 3. The opposite obviously is different. In this case, the direction is opposite. Therefore, this will become negative A. So when the angle between two vectors is 180 degree, then we pick up a negative sign. So the negative sign is always associated with the direction, never with the magnitude. All right, so let's use another board and let's draw our two vectors given to us. Vector A, magnitude 3, direction 30, so roughly somewhere here. Vector B, magnitude 4, direction 180. Therefore, B is right here. Okay? So, the problem is asking us to add those two vectors. Oh, wait, I'm sorry. To multiply a vector A by 2 and to minus B. And then they want us to get the magnitude and the direction of that new vector C. So the reason why we need to practice those is because we will have to add or subtract or multiply vector through the whole semester. So we need to know how to do this. The two only methods that we have to be able to add vectors, which will allow us to add velocity, to add forces, etc., is to express them into two forms, either the component notation or the unit vector notation. And I will start with this one. Component notation looks like this. Vector A is equal to AX I plus AY J. Some people may want to go faster, skip the I and the J, and write it like this, whatever rock you votes. This is what we call the unit vector notation. You will notice that the vector has a little arrow. I will be anal about the way you write your math, so please pay attention. Writing math correctly will allow you to do good science. Writing your math sloppily will cause many, many problems. It's like, think of it as a language. If you write in English and you can't spell any of the behavior of the two words, then the person who's going to try to read you is going to be like, what are you talking about? So, same thing. CN stands for component notation, and UN, unit vector notation. So, component notation means that we can express a vector A or any vector and decompose it into n number of dimensions. In this case, we're working in 2 dimensions, x, left or right, and y, up and down. Therefore, since I, as we've seen earlier, is the unit vector on the x and j, the unit vector on the y, A can be decomposed into 2 components, the I term and the j term. By that, do you mean by how the arrow is drawn, by the direction is put on the variable in the equation? Are you referring, Michael, to the direction of the arrow on top of my variable? Okay. The direction of the vector shouldn't influence the direction of your arrow on top of the variable. That is, we will not write B like this. Neither will we write A like that. They're always going to be horizontal towards the right. All this little arrow tells us and reminds us is that we're dealing with a vector. Does that answer your question? Did you answer your question correctly? I'm not sure I did. Oh, okay, perfect. So if you see this, A, you know it's a scalar. You know it's a length. Cannot be negative. But if you see this, you know I'm talking about a vector. If you don't like the arrow is too long to write, just put a bar. I don't care. Or a bar under. Whatever. Just make sure you distinguish it from a scalar. Okay? Now this is a little bit different. Those are not arrows, those are little hats. But as we mentioned earlier, if you see a vector that doesn't have an arrow on top but a little hat, it tells you nothing more that this little vector has a length of 1. That's all. And we have to remember that the I is reserved for the x-axis and the j for the y-axis. As we're going to introduce one more dimension, which is the z direction, we're going to use k. No biggie. Alright, so this doesn't have any arrow on top. Therefore, this is a length. This is a vector, a length, a vector. So let's represent this graphically. This is my vector A right here. I can decompose any vector into any dimensions. In this case, we're dealing with 2 dimensions, x and y, or left, right, up and down. So you could decompose, okay, let's start with B. Decompose vector B such that I start at tail and I need to end at the arrow. So I can decompose vector B as vector B1, let me go all the way over here, plus vector B2. Perfectly fine. So B is equal to B1 plus B2. You can decompose that vector B through any other points. let's say that point, B1 prime, B2 prime. So you can decompose a vector that you have into any number of vectors. In this case, I use 2, but you could use 3, 4, 5, 6, 7, 10. Usually, we decompose a vector with the same number of terms as we have number of dimensions. That's the most useful. Since we're dealing with a 2D problem, we're going to decompose in two dimensions, so 2 terms. And we're going to be clever, and for us to be able to use all the trig that we use in Math 140, we're going to decompose all of our vector in such a way that the 2 vectors we're going to use, B1 prime, B2 prime, or B1 and B2, are going to be perpendicular to one another. Hence, I'm going to decompose vector A as AX and AY. So, since AX is along the X, AY is along the Y, bang! I have identified a right angle triangle, which will allow us to use all the trig, because this is my angle 30. So that's the trick. We can decompose a vector into any amount of vectors in any direction, but for us, whether it's 2D, 3D, or 4D when you do special relativity, well, not for the fourth one, you would want to decompose, pick a coordinate system which is orthonormal, and decompose your vectors such that every vector decomposition are perpendicular to one another. So according to this, and using the same recipe, vector A is equal to AX plus AY. So not only I want to make sure that those 2 guys are perpendicular to one another, but to ensure this and make my life easy, I want to make sure that one of them is along my X and the other one is along my Y. All right, now let's go one step further. Let's compare those 2. This and this. They should be the same. If they're the same, then really this term is equal to that term, and this term is equal to this term, which means that AX is equal to magnitude AX times I. Well, let's look at the graph. This is my vector AX. We know he has a subscript X, therefore we know it's along the X axis. And we know that the unit vector for X, we talked about this, was I. Therefore, really, what we're doing here is we're multiplying a number by a unit vector to give us the full vector. For example, it could be 1, 2, 3, 4. In this case, AX could be 4I. Okay, similarly for AY, let's say we had 2, then AY will be magnitude AY, which is the length of this distance, just a length, just a number, in this case 2. And we need to know its direction. Since AY is vertical, which is a line along Y, then we're going to use the unit vector for Y, which is J by convention, therefore J. So, 2 different notation to express the same thing. This is the component notation. This is what I call the unit vector notation. What's the difference between the 2? Well, the component notation allows us to decompose of any vector into 2 components. So as we look at it, we know its X component and its Y component. But we may not know its full magnitude. For example, another board. If I tell you that vector C is equal to 2I plus J, can you give me its magnitude? Can you give me its direction? Well, I'm sure it's somewhere down there, but we have to take another look. It's not, that obvious. That information is hidden there, and usually this is the one we're interested in. But remember, since we decompose any vector into a right angle triangle, if this is C, this is CX, and this is CY. Therefore, this length here is 2, and this length here is 1. 2 and 1. Therefore, since Cx and Cy are perpendicular to one another, we can use the Pythagorean theorem that tells us that the magnitude of C is nothing else but 1 squared plus 2 squared square root. Done. And its direction is nothing else but 1 or arctangent of 1 over 2. So those are the two properties of the vector, remember? Magnitude and direction. In component notation, the information is in there, but we need to use Pythagorean theorem in 2D to extract the information. The advantage of unit vector notation, R is equal to RE, E being the generic unit vector, is that we have separated its magnitude from its direction, and it's right there. So if we need it, bing, bam, boom. For an E might be, I don't know, 0 point or 1 over square root of 2 I plus 1 over square root of 2 J. So this is the direction, and this is the magnitude. So the advantage of unit vector notation is we can extract the magnitude automatically. Now, of course, as we've seen in the previous board, for vectors that are aligned along our x-axis, it's trivial. Obviously, the length of AX is 4, 1, 2, 3, 4, bing, bam, boom, that's it. And the length of AY is 2, trivial. Okay? So, later on Wednesday, we will go over how to go from one to the other. Meanwhile, for today, let's concentrate on the component notation. So, in order for us to express any vector in component notation, there is one thing that we need, or two things. First we need is magnitude, and we need its direction. But there is something very important with the direction, which is that the direction that we need must be the direction between u vector and either the x-axis or the y-axis. It has to be. If you don't have that, you can't do it. So that's the first thing you need to look for. If you want to express any vector in component notation, you need to have the length of the vector given to you and its direction. And more important, the direction needs to be between your vector and either x or y. In this case, as I mentioned earlier, if you only be given the direction without any explanation, you can always assume it's from the positive x going counterclockwise. Therefore, you know right away this is 30. Once you have identified this graphically, the problem is done. All you have to do is identify your right-angled triangle. This is going to be your AY. This is going to be your AX. And now we can use Pythagoras. If we know the length here, which is 3, then we can deduce the length of AX. Magnitude of AX will be 3 cosine 30, because AX is the one adjacent to the angle, therefore cosine. That's why we're going to use cosine 140. And for AY, the length of AY is opposite to the angle, therefore AY is equal to 3 sine 30. And remember, those are scalar, those are positive, they represent the length. Now we need to check the signs. So as we take this information and complete the functional form of A in component notation, now when you look at the direction of our little arrows, AX is going towards the right because my arrow is right here. My positive X is towards the right. Therefore, AX is positive. This must be positive. Similarly, AY is going up. My positive Y is up. Therefore, in this case, AY is also positive. Okay, that's it. So the key is to identify your right-angled triangle. Let me show you a quick other example. If now you have B 45. The angle that defines B is between B and X. Therefore, you're going to decompose your angle like this, X and Y. BY, BX. Now let's write B. The X component, which is BX, is the adjacent to the angle 45. Therefore, it's going to be cosine. So it's going to be magnitude of B times cosine 45. And then BY is the opposite to the angle. Therefore, sine. And now we check the signs of each. Bx is going right, positive x is right, therefore positive. Now look at by. By is going down, opposite to our positive convention. Therefore, you add the negative sign. Okay? So 2 steps. First, identify the angle between your vector and either the x or the y. In this case, we use x. Then identify whether UAX is the adjacent or the opposite. That will tell you whether you're going to use cosine or sine. So that's Math 140. And then last is to look at the direction of your little arrows and double check your arrow's direction with your coordinate system. So that implies that you need to have a coordinate system. You can't do anything with a coordinate system. If I don't see a coordinate system in your work, I'm just going to look at the answer. I won't even bother. If the answer is correct, no worries, you get full points. If the answer is not correct, you get 0 points. That's from the non-WI. WI will have no choice but to show me all the steps. Somebody is pointing at the plus. Why did I put a plus? Because my BX starts here and ends here. So it goes towards the right. And my positive X is also towards the right. Therefore, this must be positive. And I put the negative sign here instead of a positive sign because my BY starts here and ends here. So it's going down. But my positive Y is up. Therefore, it must be negative. Does that make sense? Excellent. Perfect. Now, obviously, you're not bounded to one angle. There is such a thing in mathematics, Math 140, as complementary angle. So, instead of identify the angle 30, you decide, or screw this, I identify angle 60 first. So instead of identify the angle between your vector A and the x-axis, for some whatever reason, physical constraint or whatever is given to you in the problem, you have identified or you're given the angle between the vector A and the y-axis. If that's the case, no problem. Decompose your vector that includes that angle, such that your right angle triangle, as it includes your angle, will start with AY first and AX after. So the only difference by choosing a different angle is instead of doing AX plus AY, you're doing AY plus AX. Good thing is, it doesn't matter because vectors commute under addition. So AYJ plus AXI is equal to AXI plus AYJ, same thing. Now here, as you look at this right angle triangle, then same technique. AY is not the adjacent to the angle. Therefore, AY is 3, since it's the adjacent, it's going to be cosine of 60. And as to J. And UAX, in this case, is the opposite to the angle 60. Therefore, it's going to be sine times the magnitude, and that's the I vector. Now, similarly, let's check out the signs. AY is going up, positive Y is up, therefore positive. And similarly, AX is going right, positive X is right, therefore AX is positive. Those two are equivalent because 60 and 30 are complementary to one another. So the cosine of 30 is the same as the sine of 60, and vice versa, the sine of 30 is the same as the cosine of 60. So that's perfect. All those tools are like perfect for us. So you can pick whatever right angle triangle you want, but make sure that you identify it and are very clear about which one you're going to use. So obviously, if I'm asking you for the magnitude of whatever vector, everybody should have the same answer. But your decomposition might be different depending on which angle you decided to pick. Okay? So, now that we've viewed a little bit all those stupid angles, let's go back to our original problem. A was like this, 30, 3, and B was like that. Can you give me vector A in component notation? Oh, you did! Oh, let me know at 7. Thank you. So I guess I shouldn't complain about those guys. I'm just a dumbass. Oh, thank you, thank you, thank you. So, meanwhile, give me A. If you know LaTeX already, give me your LaTeX notation. Or at least give me AX. So we know it's going to be blah blah I plus blah blah J, right? What is blah blah I? What is the AX component? If A is equal to 3 and angle is 30, following the exact same technique. Done. We just did this. Everybody should be typing. Yeah, excellent. Magnitude times cosine. Excellent. Thank you. Perfect. Thank you, Tyson, Cynthia, Michael. We know it's cosine because AX is the adjacent. Thank you, Michael. Thank you, Michael. Now, once you figure one out, hey, save time. Oh, why 3? Because the magnitude is 3. We're doing problem 1. Sorry, I went on a tangent. Okay? So if you identify that the I is a cosine, save time. You know the next one gotta be a sine. They cannot be both cosine or they cannot be both sines. So up, you save time. Exactly, 3 sines. Thank you. So now all we have to do is figure out the sines. And that's where drawing down helps. So please, at the beginning, draw them on paper. That will help you figure out the sign correctly. After that, once you got practice, you're just going to do it in your head. You're going to have little vectors which that's AY, that's AX. They're both positive because they go towards a positive X, positive Y. Done. Now, question for champion. Give me B. Given that B was 4 and 180. And this is going to screw all my right angle triangle technique, but as you will see, when your vector is along any of the axes, we don't need the triangle. Because we know that cosine of 0 is 1, sine of 0 is 0, cosine of 90 is 0, sine of 90 is 1, cosine of 180 is minus 1, sine of 180 is 0, cosine of 270 or minus 890 is 0, and sine of 270 or cosine of 270 is... Wait, I messed it up at the end. But anyway. So is it 4 or negative 4? Yeah, remember all those easy angles. 0, 30, 90, then you can deduce 60, 45, those. Excellent, negative 4. Do we all agree on how negative 4 came about? 4 is the magnitude, and the negative sign comes from, it cannot come from the magnitude, right? Because we know it's always positive. Excellent, I am. Direction. It must have comes from cosine of 180. Yee-hee! Perfect. And the reason why we have 0 here is because the 0 comes from sine of 180. Perfect. Perfect, perfect. Good. So, obviously, as we've seen, when a vector is along either ux or uy, you save a lot of time. You don't have to worry about the stupid right angle triangle. So, when you are given a problem, not in the first test on the vector problems, but later on in forces, Newton, energy, where you're going to be able to pick whatever coordinate system you like, you want to make sure that you rotate your coordinate system such that the most amount of the forces given are along either x or y, so that your algebra or your calculus is much faster, much easier. Perfect. So now let's do the last step. Oh wait, no, 2. Next step. C is equal to 2a minus b. This is the trivial part. Once we have expressed a and b in complementation, adding them, multiplying them by scalar is trivial. 2a, we just multiply the whole thing by 2. And we use the distributive rule, same as algebra. And when we add them or subtract them, we go by component. We cannot mix I and j together, the same as in algebra you cannot combine x and y. So you add all the i's and you add all the j's. That easy. So in this case, it would be 6 cosine 30 minus negative 4. That's your I for C. And similarly, 6 sine 30 minus 0. Yeah. Thank you, Henry. Yeah, with a positive 4. Perfect, perfect, perfect. Now be careful. When you combine those two, you can only obtain 10 cosine 30, Michael, if the 4 multiplied by cosine. Excellent. Okay, good. Perfect. Now at this stage, feel free to plug numbers in your calculator to have, short numbers. Let me cheat and bust up the answer. Solution. Right. So if we plug this in the calculator, we're going to end up with 9.2 and 3. Okay. So now last step is they want us to deduce the magnitude and the direction. That's when we go back to Pythagorean theorem. Now graphically, let's get a feel. 2a, 1, 2. That's what a multiplier does. Minus b. So really, our vector c got to be from the beginning to where we end up. Got to be somewhere here. So it's always nice to sketch it. So we expect this to be positive and this to be positive. Sure enough, 9 and 3. So our next stage is to just deduce the length of vector c. This is cx. That's 9.2. And this is cy. That's 3. So remember Pythagorean theorem, if you have a, b, c. If you have b and c, you can deduce a. Same thing here. Magnitude of c is just going to be 9.2 squared plus 3 squared, square root. Bing, bang, boom, done. And the angle is going to be the arctangent of the y divided by the x. 3, 9.2. That's it. So now we know how to add and combine vectors, and we know that for us to do this, we need to express them in component notation. Okay? Now, there is a little problem that you may encounter, especially if your calculator is not a fancy one. If your angle is here, oh wait, let's vector A, and you end up with A is equal to negative 1 plus 3j. And as you calculate the direction of A, you end up doing arctangent of 3 divided by 1, right? Negative 1. Can anybody calculate this for you, for me? Can anybody type this in their calculator and give me whatever they give you? All right, negative 1.25. What? Wait, I think you're in radian. Negative 71. Try switch your calculator to degrees, Cynthia. Negative, let's say 71. No problem. We'll switch them back to radian in chapter whatever, rotation. Can this possibly be true? Is the direction of vector A negative 71? Remember, the convention is if you start from positive x going counterclockwise, your angle is positive. If you go clockwise, your angle is negative. There is no way, right? Okay, so we need to fix that stupid calculator. If your vector is in the first quadrant, no problem. You're good to go. If your vector is in the second, third, or fourth, you're toast. So we have to do 2 more checks. But the method is easy. First, identify in which quadrant your vector is. To do this, identify the signs. Positive I, positive j, first quadrant. Negative I, positive j, second quadrant. Negative I, negative j, third quadrant. and positive I, negative j, fourth quadrant. Okay, so the signs will tell you in which quadrant you're in. That's the first step. Once you know which quadrant, then forget about the numbers and the sign that they give you. Just look at the absolute value, 71. So now you know that A is negative I, positive j, so you know it's in the second quadrant. The next question is, where the heck is 71? Is 71 between your vector and y, or 71 between your vector and negative x? The next test to figure that out is, instead of focusing on the signs, focus on the magnitude. 3 is for j, while 1 is for I, which means we're going 1, 2, 3, and only 1. Therefore, the higher number, the closer your vector is to this unit vector associated with it. Therefore, vector A is, in this case, closer to the j vector than it is to the I, because 3 is bigger. Hence, 71 given to you must be this vector, because halfway is 45. Done. Now you have the right angle. So now in your answer, you either say, okay, my answer is 71, but it has to start from negative x going clockwise. Or you use the convention by just giving a number, but it implies that you start from a positive x going counterclockwise. Therefore, you need to do 180 minus 71. And this will be your answer.